Day 2, exponential functions. Identify and evaluate exponential functions. Today you will be able to write and graph exponential functions involving real-life scenarios.
Years ago, there were only 1/3 of a billion people, but we were multiplying. Now there's 7 billion of us. How did we grow so much, so fast? Say this glass is North America. The fuller the glass gets, the more people there are. Water drips in as people are born. Water drips out as people die. Okay, here's the entire world. Now let's go back 1,000 years. The Americas are nearly empty. Europe and Africa have less than 100 million people between them. And just like today, most people live in China, India, and the rest of Asia. For centuries, things stayed pretty much the same. Births are canceled out by deaths. Women are having lots of babies, but most babies die before they grow up and have families of their own. We don't reach 1 billion until 1804. But things are changing. Better medicine and better agriculture are starting to slow the leak from the bottom of the glass. People still die, of course. But more babies grow up and have babies of their own. Lots of babies. Grown from 1 billion to 7 billion, and it only took 200 years. Will we keep going like this? Probably not. The UN says we'll level out at 10 billion by the end of the century. So as we continue to grow from 7 billion, the question is, can the world hold that many people? Experts can't agree. It all depends on how well we manage our food, water, and energy.
So when we looked at that video, that was an example of exponential growth. So we had time and days, and we look at the population if we take a look at this chart. So our population, if we went from 2 to 6 to 18 to 54, is multiplying each time by 3. So if we write a rule for this pattern, we would write the function of x is equal to 2, which was our starting population. The amount the population is multiplied by each day goes in this parenthesis, which was 3. And then our exponent is a variable. We can also take a look at this chart to our right, and you can see this chart demonstrates the insect population. And you can see it's starting off small, but it is increasing at a very fast rate. These are examples of exponential functions. An exponential function has the form f of x is equal to a times b raised to the x power, where a cannot equal 0, b cannot equal 1, and b has to be greater than 0. So in order to identify whether something is an exponential function or not, we can ask ourselves, how are we moving from one spot to the next? So when we move from 0 to 1, we are adding 1. 1 to 2, we're adding 1. 2 to 3, we're adding 1. When we go from 2, 4, 6 to 8, we're adding 2 each time. So if we put the rate of change, or the change in y, over the change in x, and we take 2 and place it over 1, our rate is the same for each of these numbers, and we are adding to get to our next term. When we take so this would be an example of a linear function. And linear is because we're adding. Looking at the next chart, to go from 0 to 1, we add 1. 1 to 2, add 1. 2 to 3, add 1. But when we look at our y's, to go from 4 to 8, we either add 4 or multiply by 2. And it's really important that we have to do the same thing from one term to the next. So if we add 4 to 8, it wouldn't get to 16, but if we multiply 8 by 2, it gets to 16. If we multiply 16 by 2, we get 32. So when we are using multiplication to get from one term to the next, we are talking about exponential functions. So in order to evaluate an exponential function, we want to take a look at our initial amount. So 500 in this example would be our initial amount. And then let's take a look at the problem. It says the function f of x is equal to 500 times 1.035 raised to the x power. It models the amount of money in a certificate of deposit, which is also referred to as a CD, after X years. How much money will there be in 6 years? So they told us that our years is represented by 6, so we're going to plug 6 in for our exponent. We're going to follow our order of operations, so we're going to multiply our exponent first, then times that by 500, and we get a total of $614.63 would be in our savings. The next function says f of x is equal to 200,000 times 0.98 raised to the x power, where x is the time in years that models the population of the city. What will the population be in 7 years? So they told us that x is the time in years, and we want to evaluate that for 7. So in our function, we are going to plug 7 in for x, type it into our calculator, and simplify. So 0.98 raised to the 7th power, you can use your caret key, then multiply that by 200,000, and our calculator tells us that we have 173,625 people in our population. So let's look at the variations of an exponential graph. When we look at the graph of y is equal to a times b raised to the x, when b is greater than 1, our graph is either going to be increasing like this blue line, if a is greater than 0. If a is less than 0 or a negative number, it's going to be decreasing. Looking at our other slide, if a is greater than 0, but now we're talking about a b that is between 0 and 1, it's going to start high on the left and get lower or decrease to the right. If b is between 0 and 1 and a is negative, our graph is going to start lower on the left and rise to the right. So to graph an exponential function, we need to choose several values for x. So the most common values that we choose are -2, -1, 0, 1, 2, 3. And then we're going to plug those values in. So 0.5 times 2 raised to the -2nd power, when you type that into your calculator, you get 0.125. 0.5 times 2 raised to the -1st, we get 0.25. 0.5 times 2 raised to the 0 will give us 0.5. 0.5 times 2 to the 1st gives us 1. To the 2nd gives us 2. And when we plug in 3 for x, we get 4. So we can quickly graph those numbers. At -2, it's really close to our x-axis. At -1, we're about 1/4. At 0, we're at about 1/2. At 1, we're at 1. At 2, we're at 2. At 3, we jumped up to 4. So you can see that our graph is approaching our x-axis but not touching it. And it is increasing at a very fast rate. So the domain, when we look at this graph, or we look at our x values, we're going towards negative infinity on our graph. And then we're also going towards positive infinity because this line is going to continue up and up. So we can say that our domain is all real numbers. In our range, we look at our y-axis. So it's never going to touch my x-axis. So we want all the y values that are greater than 0. Let's take a look at example 4. So now we're talking about the graph of y is equal to negative 1/4 times 2 to the x power. So please remember we want to pick some values for x. So negative 2, negative 1, 0, 1, 2, 3. And we're going to evaluate these. So we are plugging our numbers in for x in the equation above. And we're following our order of operations. So 2 to the negative second power times negative 1/4 is going to give us a negative 0.0625. Negative 1/4 times 2 to the negative first power is going to give us a negative 0.125. When we plug in 0, we get negative 0.25. When we plug in 1, we get negative 0.5. When we plug in 2, we get negative 1. When we plug in 3, we get negative 2. If we want a better look at things, we can plug in 4 and 5. When we evaluate for 4, we get negative 4. When we evaluate for 5, we get negative 8. So if we plot these points on our coordinate plane, you can see that our values, 2, negative 1, 3, negative 2, begin to increase at a very rapid rate. So again, it's coming from my x-axis but never touching it, and it's getting very big very quick. So the domain for this graph, if I'm talking about my x values, I'm going from negative infinity to positive infinity, which means our domain is all real numbers. And our range in this one, if we're looking at our y values, so where do we start, where do we end? Well, we get close to 0, but we don't touch it. And we go to infinity, so we want all the y values that are less than 0. You now can complete your day 2 worksheet.